All right, new section here. This is the last section in this block that I call Intro to Integration. After this, we'll move on to what I think I called Advanced Techniques of Integration. And essentially, what that comes down to is more challenging integrals. And you're like, what do you mean more challenging integrals? Well, most of our work on evaluating integrals comes down to taking an antiderivative. And at this point, all the functions that we're asked to take antiderivatives of are fairly straightforward. And I mean, you might argue that some problems in the 4.8 homework were a little bit challenging, or the 5.3 homework for that matter. But you've never had to like undo the chain rule or undo the product rule or advanced stuff like that. What we'll learn in the next block is precisely that, how to undo these more complicated rules that you learned in Calculus 1. But that's all for the next video. In this video, I want to finish up this intro to integration with a topic that's called the fundamental theorem of calculus. So just kind of based on the name itself, it might seem really important. I don't know, you could argue its importance. That doesn't really matter. Maybe without further ado, I should just tell you what it is. Actually, there is further ado because there's a little bit of housekeeping that I want to do before I talk about the fundamental theorem of calculus. And really, it just comes down to naming conventions. Most books, yours included if you kind of read the fine print, says that there's two different versions of the fundamental theorem of calculus. Or maybe precisely, the fundamental theorem of calculus has two separate statements. And what we're going to learn in 5.4 is the first statement of the fundamental theorem of calculus. You're like, when am I going to learn the second statement of the fundamental theorem of calculus? Turns out you already have. The evaluation theorem that you learned in 5.3 is also referred to as the second statement of the fundamental theorem of calculus. I think that can be really confusing, and I guess your book does too, because it only mentions that they're both technically the fundamental theorem of calculus in kind of the margins. But as far as the chapter headings go, they call one the evaluation theorem and the other the fundamental theorem of calculus. So that's what I'll do to try to make your life easy. We'll just refer to this one as the fundamental theorem of calculus and the other one as the evaluation theorem. But I felt guilty not letting you know that technically they're both just statements of what's referred to as the fundamental theorem of calculus. Moving on, what is the fundamental theorem of calculus? Well, the idea of this is we want to relate together the key ideas of Calculus 1 and Calculus 2. Stating the key idea of Calc 1 is fairly straightforward. I think everyone would pretty much agree that what you learn in that class is about the derivative. You learned how to figure it out using the difference quotient and the definition of the derivative. Then you learned these shortcut methods, all these different rules. Then you learned applications of it. Really, the whole course was centered around this one idea called the derivative. You have a function and you want to know about the rate of change of that function, the slope of the tangent line to that function. All these ideas that you learned in Calc 1, all centered around the derivative. Calc 2 is a little bit less obvious, because in Calc 2, you'd argue that it's the integral. And I'd say that it is. I mean, everything we're doing is the integral, but it kind of takes on lots of different forms. Right? First, we learned about antiderivatives, and then we learned about the definite integral, and we've talked about the indefinite integral, which is really just another way to talk about antiderivatives. So you're like, what do you mean when you talk about the integral? Well, really, the key problem in Calc 2 is the area problem. How much area is there underneath the curve? We haven't gotten into application, so you don't really understand or you haven't seen the importance of answering that question. But all of Calc 2 comes from trying to answer that question. And to figure out how much area there is underneath the curve, you have to evaluate what's called the definite integral. And yeah, to evaluate the definite integral, you need an antiderivative, so you need the ability to figure out an indefinite integral. That's all true, but it's all centered around this idea. So what we want to do with the fundamental theorem of calculus is tie together the derivative and the definite integral. And that's kind of unfortunate because it's easier to tie together the derivative and the indefinite integral, because the indefinite integral is just the antiderivative, and tying together the derivative and the antiderivative, well, that's fairly easy, right? They're just kind of opposites of each other. One gives you little f of x and takes you to capital F of x. The other gives you capital F of x and takes you to little f of x. But when you're trying to tie together the derivative with the definite integral, it's a little bit more challenging, because remember, the definite integral, typically your answers have been a number. Remember this example that we spent so much time on? How much area is there underneath the curve x cubed between x equals 2 and x equals 5? Right, that's a definite integral. And this answer is a number. Let's see how good my memory is. 609 divided by 4? I don't think that's right. Whatever. Something like that. How do we tie together something like this that takes in a function and gives out a number with something like the derivative that takes in a function and gives out a function? It might seem a little bit contrived. It might seem odd what this statement is saying. And it is a little bit contrived. It's a weird situation. Often the question that students get when they're done with 5.4 is, okay, I guess I can do that, but why? And I'm not sure I could provide you with a great idea of why. The reason it's taught is to try to strengthen your understanding between these two concepts. Here is the formal statement of the fundamental theorem of calculus. And it looks pretty confusing, so let me try to talk you through the whole thing. What we're going to do is we're going to define some function, we'll call it g of x, that's going to be defined as the definite integral from a to x, which is a little bit weird. X is the variable here. We're used to saying constants here and here. In this case, we're going to have a constant here and a variable here, and I'll explain why. Anyways, we're taking the definite integral of some other function, and that other function's argument is t, as opposed to x, which is already a little bit strange. I'll explain why we have to do that. At any rate, if we define this function g of x in this really strange manner, then the derivative of this function, g of x, is just equal to f of x. Like it's just this, well, except you changed the letters on me for some reason. Yeah, that's exactly it. Informally, what we're saying here is the integral that I introduce right here and the derivative that I do right here are going to kind of cancel out, right? This will stay more or less the same. F of t stays as f of t, except now for some strange reason it's f of x. So if I take the derivative of this thing that involves this definite integral, the derivative and the integral part cancel out, and I'm left with just this function that I began with. That's the formal way of connecting together the derivative and the definite integral, which is called the fundamental theorem of calculus. Okay, what's going on here with all the letter changes? First off, remember the big challenge with connecting the two of these guys is the definite integral, we're used to it supplying numbers. But that's problematic. If we want these two things to be inverses of each other, we can't have this give a number as its output, because this takes in functions and gives out functions. Think this picture, right? The derivative of this function, which maybe I'll refer to it as capital F of x, is just little f of x. It takes in a function and gives out a function. So the inverse is going to have to take in a function and give out a function as well. But we're not used to that happening with a definite integral. With a definite integral, we're used to taking in a function like x cubed and giving out a number like, I can't remember the number, 609/4 or whatever the heck this was. So what we need to do is change the way we think about definite integrals to have a function come out of the definite integral as opposed to a number. Well, how are you going to do that? Think about your evaluation theorem. It says that the definite integral of a function is equal to the difference in these two antiderivatives, right? This is what our evaluation theorem told us. So what we need to do is make this output right here a function as opposed to a number. How are you going to make this a function? Well, stick a variable right here. Right? Because if you think about how you would evaluate this thing, step one would be to figure out capital F of t, and then step two would be to change all the t's into x's, and then change all the t's into a's, and subtract those two things. And the advantage to doing that, where I change all the t's into x's, is that will leave me with a function, capital F of x. Not following? Good. You're not supposed to be. Most people aren't following this at all. Totally fine. Let me give you an example, and we'll come back to this and hammer it a few times until it makes sense. Here's your standard fundamental theorem of calculus question. What it says is we're going to define this function g of x, and it's going to be equal to, in this case, the integral from 2 up to x of t cubed dt. And it still feels weird that I got x's and t's floating around, but maybe when I actually solve this, you'll see the necessity for both of them. And what I'm asked to do is find g prime of x. It's worth pointing out that the answer to this question is given by the fundamental theorem of calculus. Right? The answer is easy in these problems. What I'm asking you, the student, to do is show why this works. Show why the answer is just, in this case, it's going to end up being x cubed. So suppose you're given this question. Let's go through the steps. If g of x equals the definite integral from 2 to x of t cubed dt, I can use the evaluation theorem to rewrite this. I can say g of x is just, I could deal with this left-hand side, right? I have some function d cubed and my variable of integration is t. And what I want to do is figure out the antiderivative of that. The antiderivative of t cubed, that's pretty easy. I just add 1 to the exponent and get t to the 4th. But then I have to not forget to put the 1/4 out in front. So there's the antiderivative, but then I'm not done. I have to evaluate that from 2 to x. Right, from this 2 to this x right here. And that's all easy. All I got to do is copy this, except change all the t's into, well, first x's and then 2's. So I'd get 1/4 x to the 4th power minus 1/4 2 to the 4th power. And if you feel the need, you can note that 1/4 2 to the 4th power is just 4, because 2 to the 4th is just 16, 2, 4, 8, 16, and 1/4 of 16 is just 4. What I'm saying is you can rewrite this way if you want, or leave it here, it really doesn't matter. And you're like, that's my answer? No, that's g of x. Right? All I'm doing is I'm rewriting g of x. G of x was stated this way, And because I'm an expert with the evaluation theorem, I have no problem saying, well, that's just equal to this thing down here. But I'm not done. I want to find g prime of x. Well, if g of x is this thing, g prime of x is just the derivative of this thing. Think calculus 1. The derivative of a sum of two terms. Well, this one is just 0. I can ignore that. I can take the derivative of each term individually. And then the derivative of this one, well, I guess I'd bring the 4 down in front and subtract 1 from the exponent. So I'd have 4 times 1/4, which is just 1, times x to the third power. G prime of x is just x to the third power, and I'm done. What I just did here was illustrate my knowledge of the fundamental theorem of calculus. It's worth pointing out that this final answer is not that impressive because you already knew this answer. It's just the same as the question. Whoa, what just happened there? Remember, the fundamental theorem of calculus is saying that if you're set up in this contrived feeling situation, this thing right here is just your answer. If somebody asks you the question, what's g prime of x? Your answer is just, well, it's this thing. I mean, change your variable from t's to x's, right? Don't write t cubed, write x cubed, because it would be weird for g prime of x to be equal to t cubed, right? This is a function of x, so my variable should be an x, not a t. But all you have to do is take whatever's written right here and put that down here as your answer. That's the fundamental theorem of calculus. 99% of students are scratching their head right now like, I don't quite get it, and I certainly don't get why. Okay, the why is harder for me to argue for. The why is it's supposed to give you a deeper understanding of what we're doing, right? We want to make the point that the derivative and the integral are inverses of each other, loosely speaking. In order for them to be inverses of each other, if we do both of them one after the other, they should kind of sort of cancel out and leave us where we began. If we start with this function f and we do the integral to it, and then we take the derivative of it, it should leave us back where we start. But it's a little bit hard to describe the exact relationship between these two, describe this exact inverse relationship between the derivative and the definite integral. And in order to describe this exact relationship, we need to set it up this way. In this section, expect a lot of questions that look like this, although what we'll see in the next video are there little tricks and twists we can put on them to make your work a little bit harder. But this is the basic setup where you have some function that's defined to be the definite integral of some other function, and then you're asked to find the derivative of that first function. And what you'll see is these are the easiest answers to check ever, because you know what the answer should be before you start. You look at this, you know the answer should be x cubed. It's just this t cubed, except change all the t's into x's. Why? Because the answer is just f of x, and f of t is given to you in the problem. I really wish we were in a classroom and I could look at your faces to see if you're still confused or if this is making a little bit more sense now. Maybe I should just do more examples. Actually, I'm going to save the examples for the next video. Just one last point that I want to make. Something that always bothered me with this was the change in variables. Everything's x is floating around here except this t. Why do you need a t there? Couldn't you just make this x to make my life easier? The reason you can't is because you need an x in this spot right here. Right? You need an x in this place. If these are both just constants and your x is down here as we've seen before, then your answer is a number. I need my answer to be a function, not a number. In order to make my answer a function, I need there to be a variable here, not a constant here. The way I put a variable here is I put a variable right here. So I need there to be an x right here. And you're like, well, I don't know. Why not just have x's in both places? Well, that wouldn't make much sense. What this is really saying is you have some function. In my picture, that function is f of t. This is the t-axis here. And I want to know how much area is there underneath this function, starting at some constant a, so in your head like the number 3 or something, starting somewhere, and ending at a variable. So this is a function that kind of tells me the area so far. I can make my variable whatever I want. The t value is changing. So maybe first the t value is a 4, and then the t value is a 5, and then the t value is a 7, and then a 12. I'm going to let that t value change, right? Maybe you could think of it as being here, and then later here, and then later here. This is moving. And as this moves, the area underneath this curve also changes, right? In my picture, as x denotes larger values of t, the area underneath this curve gets larger and larger. So this is kind of an area so far function. The reason I can't just put an x here kind of just comes down to notation, right? I can't put an f of x here because then I'm calling this axis my x-axis, and it doesn't make sense to say that my area so far function ends at x, because every value is x, because this is my x-axis. So I just need two different ways to refer to this axis so that I can talk about a specific value on that axis. So don't let the fact that this is a t throw you off too much. It's just a way for this statement to make sense. This statement has no meaning if this is f of x dx and this is an x right here. It just doesn't make sense mathematically. I know this is confusing, but hopefully you're starting to get a little bit of a feel about what's going on here, and I'll give you a lot more examples in the next video, and we can hopefully tie some of these ideas together. Unlike most of Calc 2, answers in this section are easy. It's easy to come up with x cubed, but understanding what you're doing, that's what really takes a little while. So if you can just get the answers at this point, and you're starting to kind of sort of understand the purpose of this whole thing, that's awesome. We'll get further in the next video.